Let's take a look at example 5. We have the parametric equations x equals cosine of t and y equals sine of t. We want to graph individually what these two parametric equations look like on the tx and the ty axes, and then we want to sketch the entire overall curve in the xy plane. So our x function, x is cosine, and the y function is sine. Now, for this particular problem, I don't think it's very useful to set up a t, x, y table and try to plot points as we did in the previous couple examples. We're going to individually look at the curves for x and y and then try to conglomerate that information to write a parametric equation for the whole thing. So what does the curve look like for the x function? I'm going to sketch here. I have t, where the x-axis would normally be, and then I have x of t. And this is cosine. So cosine looks something like this. Now, for the y function, I'll do a similar sort of a thing. For the y function, I once again have the t-axis here, and I'm going to graph the y expression for t, and the y function looks something like this. So the x function is cosine of t, the y function is sine of t. Now, we want to choose specific values for the parameter, different values for t, and we want to imagine plotting the points from those values for t on the xy plane. So over here, we're going to draw the regular old Cartesian coordinate plane, x and y. And let's just imagine taking a couple different values here from these two different curves for the x function and the y function. So when t equals 0, we get an x value. This would be an x value of 1 and a y value of 0. So we can plot that point, x equals 1, y equals 0. And then let's choose a couple more values. At this value right here, this is t equals pi over 2. And the corresponding t value here on the y function. So when t equals pi over 2, the x value is 0 and the y value is positive 1. So we have 0 comma positive 1. That's right here. And then similarly, when t is pi, the x value is negative 1 and the y value is 0. So we plot the point negative 1, 0. And finally, if we think of 3 pi over 2, that's this t value here, 3 pi over 2, the x value is back to 0 and the y value is negative 1. So we plot 0, negative 1. And then last of all, at 2 pi, that's this t value here, at 2 pi, the x value is 1 and the y value is back to 0. So we plot the point x equals 1, y equals 0 right there. Now in between, we might be able to start to see what's happening. As t ranges from 0 to pi over 2, the x values are decreasing. So x values will be going this way as t ranges from 0 to pi over 2. The y values, however, are increasing. Y is going up as t ranges from 0 to pi over 2. So the y values are increasing, the x values are decreasing. It will look something like that. Can you see what this curve will look like? This is simply a circle. These parametric equations give us the circle. And this is actually the unit circle. Now, think about what we know about the unit circle. Maybe it's been a while since you've thought about the unit circle. But with the unit circle, if we choose some sort of an angle here, let's call this angle theta. Actually, no, let's call this angle t, because we're using t as the value that we'd normally think of theta for the unit circle. So here's an angle t. We can find the x and y coordinates of this point from the angle t by taking cosine of the angle, comma, sine of the angle. This is what the unit circle is all about. Any point along the unit circle is the x value is the cosine of the angle, the y value is the sine of the angle. That's how the points on the unit circle are defined. That's exactly what these parametric equations are giving us. We are getting the unit circle from these parametric equations. Let's take one additional step here, and let's eliminate the parameter to find a Cartesian equation of this curve. Now, it's not so useful to solve one of these equations for t, because we'd be using arc-trig functions, which doesn't sound very pleasant. So there is another way, a better way, to eliminate the parameter in this case. What we can do is use the trig identity sine squared of t plus cosine squared of t, that always equals 1. Now sine squared of t, well, sine of t is y, so instead of sine squared of t, we could write y squared. Cosine of t, that's just x, so cosine squared of t is just x squared. So y squared plus x squared equals 1. Look at this. We have a Cartesian equation for the circle, and hopefully this looks super familiar. This is the equation for the circle centered at the origin with a radius of 1. Let's take a look at these concepts in Desmos. So first of all, let's just plot the parametric equations x equals cosine of t and y equals sine of t. And let's vary the parameter, let's just say from -10 to +10. So we get the circle just as we expect. Let's look at an individual point on this circle. So we're going to enter these again and just replace the parameter with capital T. And this gives us a point that we can slide around the circle. And notice as t ranges from -10 to +10, the circle is sketched out many times. We can think of t as the angle on the unit circle. So if we only want the circle sketched out once, we need to range the parameter from 0 to 2 pi. So if we range the parameter from 0 to 2 pi, then we get the circle just traced out once. So it starts here, and we get the circle traced out exactly once. We could see the entire thing being traced out actively. If we change this upper limit to capital T, here's the unit circle being traced out exactly once as the parameter ranges from 0 to 2 pi. Finally, let's work through problem 6. And we're really going to heavily depend on Desmos to help to visualize what's going on here. So we have two particles with trajectories described by different parametric equations. So one particle has a position described by these parametric equations, and the second particle is described by these parametric equations. What we'd like to do first is just graph these equations, and we want to identify if the graphs ever intersect. So we're going to first try to think through doing this by hand, and then we'll look at Desmos for a better visualization. So it's key for this one to keep in mind what we learned in the last problem. If we looked at the functions x equals cosine of t and y equals sine of t, we would get the unit circle. These parametric equations give us the unit circle. And we have variations on that for the two different parametric equations that we have for example 6. So for the first parametric equation, we have 3 times sine, 2 times cosine. What that's going to end up doing is scaling in the x direction by a factor of 3 and scaling in the y direction by a factor of 2. So even though we flipped sine and cosine from how we had them previously, we still get not a circle but rather an ellipse. So the ellipse will look something like this. It's stretched 3 in the x direction since we multiplied by 3, and it's vertically stretched by 2. So the ellipse looks something like this. Not a very great picture, but something like that. It's stretched 2 vertically, and it's stretched 3 horizontally. That's what the graph looks like for the first parametric equations. What about the second parametric equations? Once again, we have the cosine and the sine, and now instead of multiplying, we're adding and subtracting. And essentially what that does is horizontally and vertically shifts the circle. So we're going to get a unit circle from these, but the circle is going to be shifted in the negative x direction by 3 and shifted vertically by 1. So the center of our circle will be at -3, 1. So here's -3, 1 is right there. So we have a unit circle centered at -3, 1. So this circle looks something like this. And now we can see that from these two parametric equations, there are places where they seem to intersect. So we're going to see about finding those intersection points, and we'll see if we have what's called collision points here. But let's visualize this in Desmos, because it's much easier to see what's going on when we can manipulate the different parameter values. So let's start by plotting the first parametric curve. We have the x value of 3 sine of t, and the y value is 2 cosine of t. And we're told that the parameter t ranges from 0 to 2 pi. So there's that ellipse. And now let's plot the second function, which is the circle. So the x value for this one is cosine of t minus 3, and then sine of t plus 1. So this also ranges from 0 to 2 pi. There's our circle. So we have two places where these parametric curves intersect. Now let's try to figure out if we have collision points here. So to do that, we're going to look at the specific points on these curves that trace out the curves. So for the first curve, for the ellipse, as the parameter ranges from 0 to 2 pi, here's what the point does. It starts there, moves around the ellipse, and similarly for the circle, we're going to describe the point on the circle and look at how that point moves around as the parameter changes. So we have these two different points, the point on the circle, the point on the ellipse, and as the parameter changes, as t ranges from 0 to 2 pi, these 2 points move around. Now notice here, we have an intersection point of these two graphs right there, but this is not a collision point because one of the particles is at that intersection point, but the other one is not. So everything's okay here. We don't have a collision of these two particles, even though the Cartesian graphs intersect. There's no collision because the particles are not in the same place at the same time. They'll both eventually pass through that point, but they're not at the same point at the same time. All right, so as t continues to increase, these particles keep moving around the parametric curves, and we see trouble happening. Right here, we have a collision point. The particles are in the same place at the same time. Whatever that t value is, that's creating a collision. If they continue to move around, we see we still don't have a collision at this second intersection point because the particles are not at the same place at the same time. However, right here, we seem to have a collision. Now, how could we find analytically what that collision is? It seems to happen when x equals -3, y equals 0. But what is the parameter value that gives us that collision? Well, to find that, we are going to use Mathematica. So here's Mathematica. And to find the collision points, we are going to take the x equations for both of the curves and set them equal to each other. This is similar to how we find intersection points of two regular Cartesian graphs. We would take the values of the functions, set them equal to each other, solve for x. Here we're going to take the x equations, set them equal to each other, and solve for t. So we set 3 times sine of t equal to cosine of t minus 3, solve for t, and we get these rather messy looking expressions. The reason we have these 2 pi c1 if c1 is in z, this is because there are coterminal angles that produce the same values for these different functions. So what we're interested in is the values between 0 and 2 pi. The first one happens at 2 pi minus pi over 2. So if we think of taking 2 pi times 1 minus pi over 2, that gives us the first value here. The other one happens at 2 pi minus arctangent of 4/3. So we'll do 2 pi minus arctangent of 4/3. Now I'd like decimal values here because we can use those in Desmos. So the decimal values are 4.712 and 5.355. Okay, let's go back to Desmos. And we want to look approximately at 5.355. That's right about there. Now notice that the x values on these two curves are the same. They're both at the same x value. The parameter value t equals 5.35, etc. That gives the same x values because we set the x values of the curves equal. There's not a collision here though. Even though the particles have the same x value, they don't have the same y value, so we don't have a collision. What about at this second value for t, 4.712? Well, we'll slide the slider back to about 4.7. Look at that. That's where we have the collision. So the collision happens when t, we can think of t as time here, the collision happens when time equals 2 pi minus pi over 2 or 4.712. So we get this collision point. So back to our problem statement here. We just graphed the two equations and we identified the different intersection points, and we discovered that the particles do collide if we use these two parametric equations. The particles are at the same place at the same time when t equals 2 pi minus pi over 2, which is approximately equal to 4.71. So we have a problem. We have a collision point of the two particles at this value for t. Now, let's think about changing up the second curve. We're going to change it up using different equations. So instead of using x equals cosine minus 3, we're using x equals sine minus 3. Cosine changes to sine changes to cosine. We're going to end up getting the exact same graph, but because we're redefining how it's plotted, that will change up how the point moves around the curve as the parameter changes. So let's take a look at this in Desmos. So here are our curves once again in Desmos, and we're taking the second curve and we're redefining it to be sine of t minus 3, and then the y value is cosine t plus 1. So we get the same looking picture, it's still the same circle, but we've redefined how the circle is traced out. And then let's look at how the circle is traced out with this point here. So as our parameter value ranges from 0 to 2 pi, watch the points on the two different graphs. We want to know if these points ever collide. No collision here, even though the graphs intersect. The particles are in different places at the same time. So since the particles are not at the same place at the same time, there's no collision. Okay, do we have a collision at the same place that we did before? As the parameter continues to vary, oh, everything's fine. Look at this. One of the particles is at the old collision point, but the other one is not at the same time. So even though we have intersection points of these two graphs, there's no collisions. We could think of these maybe as orbits of satellites, and it's a rather simplified view, but we could see here that even if the orbits would intersect each other, as long as the objects are never in the same place at the same time, we don't have any collisions, everything's fine. So we can redefine a parametric equation and get the same looking plot, but since it's traced out differently, we can avoid collisions like this.